If chemicals, once they formed, never changed, then the world would be a pretty boring place. Our universe is enriched by the great principle that elements and compounds combine in chemical reactions to form new materials. In this lecture, I'm going to introduce two major aspects of chemical change. The first topic is phase transitions. That's the property of some materials to alter their atomic structure when they're subjected to heat or to pressure or to some other external influence. As we'll see in this and future lectures, phase transitions play key roles in the dynamics of the Earth and the workings of life. Then I'll introduce some of the many kinds of chemical reactions by which one group of elements or compounds transforms to a completely new group of chemical substances with new properties. Chemical reactions are absolutely essential to life and all its pursuits. This lecture, then, is the real meat of modern chemistry. Change is the hallmark of the material world. Water boils, wood burns, glue hardens, eggs cook, dead organisms decay. These obvious physical transformations reflect changes in the arrangement of atoms and their chemical bonds. Now, in the last lecture, we examined changes of state between solids, liquids, and gases. Recall that we can use temperature or pressure to induce these changes. So these changes of state represent common ways to rearrange atoms from one physical form to another. In this lecture, we'll meet two other common ways of rearranging atoms. I'm going to tell you about phase transformations and chemical reactions. Now, in the past several lectures, we've seen lots of examples of how common substances can occur in more than one arrangement of atoms. In lecture 22, for example, we saw that there are a total of 18 different isomers of octane. That's C8H18. You can arrange all the carbon atoms in a straight chain. That's normal octane. Or you can have various branching arrangements with one or more carbon atoms off to the side. And each of these isomers has a distinctive set of physical and chemical properties. The change of a substance from one atomic arrangement to another, particularly from one solid form to another, is called a phase transformation. One of the most dramatic examples of a phase transformation is provided by the element carbon, which occurs naturally both as graphite and as diamond. It would be hard to imagine two crystalline compounds that differ more in their physical properties. Black graphite, it's used as a lubricant, and in pencil lead, it's just about the softest solid in the mineral kingdom. Colorless diamond, on the other hand, is the hardest known material. It's used as an abrasive to cut and polish just about any other substance. We now know that these dramatic differences in physical properties result from their distinctive atomic arrangements. Let me show you these two crystal structures, which were determined early in the 20th century. The crystal structure of graphite is marked by obvious layers of carbon atoms. Bonding within the layers is extremely strong and covalent. Each carbon atom is tightly linked to three others, but bonding between the layers is by relatively weak van der Waals interactions. That means that the individual layers can easily slide over each other. In fact, when you write with a so-called lead pencil, you're actually transferring layers of graphite onto paper. But now look at the diamond structure. It's amazingly strong and rigid. See how each carbon atom is bonded to four others in this trestle-like arrangement? The way these atoms link up, there simply are no weak directions, so diamond is hard and tough. 200 years ago, when scientists discovered that graphite and diamond are both forms of carbon, they quickly began to explore ways to transform common graphite into rare diamonds. After all, the first person to learn that trick could make an absolute fortune. And most of the early attempts focused on extremely high temperature. You see, high temperatures had long been the chemist's most reliable path to make materials change. Well, to make a long story short, the process didn't work. And what's more, the credibility of serious scientists who tried was hampered by a whole parade of frauds who would sort of magically make big diamonds in an oven and then dupe potential investors out of their life savings. That quest for synthetic diamonds was placed on a more reputable footing by Henri Moissan. Remember, Moissan was the brave French chemist who won the Nobel Prize for first isolating the dangerous element fluorine. Well, Moissan had invented an electric arc furnace to produce the highest available temperatures. When he blasted graphite, he found a few small, shiny crystals, and he became absolutely convinced that he had actually made diamonds. Others followed Moissan's lead, and a sort of cottage industry arose making these crystals. We now know that Moissan was actually synthesizing silicon carbide. That's a material that's now being marketed as moissanite. is a synthetic substitute for diamond in jewelry. As it turns out, no amount of high temperature alone can produce diamonds from graphite. The true key to synthesizing diamonds came from geology. You see, into the 1870s, diamonds were known only from gravel deposits in a few exotic locales like India and Brazil. But that diamond story changed dramatically in 1866 when two children playing in a South African streambed found a 20-carat shiny pebble. It was soon to be known as the Eureka diamond. And 2 years later, the 83.5-carat Star of South Africa was found in another streambed, and that find triggered a diamond hunting frenzy that resulted in the discovery of diamond in its native rock. That rock's a crumbly, yellow weathering material that became to be known as kimberlite, after the locality of Kimberley, South Africa. And it turns out the kimberlites were restricted to narrow, vertical pipe-like structures. Now, thousands of miners would crowd into these narrow features and started digging as fast as they could, and the result was this bizarre and chaotic landscape. It was quite dangerous for miners who dug the deepest pits. Now, geologists quickly realized that diamonds come from great depths in the earth. The rock at Kimberley and other diamond mines forms a narrow, funnel-shaped mass that extends to deep within the earth. This distinctive shape revealed that high pressure is a key to diamond synthesis. Diamonds form deep inside the earth. They only reach the surface in rare epic volcanic explosions that transport molten diamond-containing rock from 100 miles down in a matter of an hour or less. This knowledge gave scientists new insight about how to make diamonds in the lab. Using theories that relate a material's structure to its stability, scientists were able to calculate a pressure-temperature phase diagram for diamond and graphite. And here's the bottom line. Take a look at the phase diagram. Not only does diamond require pressures of tens of thousands of atmospheres, it also requires temperatures over 1,000 degrees centigrade. At lower temperatures, the carbon atoms in graphite are too tightly bound to each other to rearrange themselves. Without heat, graphite just remains graphite. So armed with this new understanding, many scientists tackled the synthesis of diamond in earnest. One of the first scientists to try pressure was the Scottish chemist James Ballantyne Hannay. And he used a simple design that's still employed today. You take your sample, you cram it into a steel cylinder like a gun barrel, you'll seal the end, and heat it to a highest temperature as possible. Here's an example of one of these steel cylinders. See, it's just like a gun barrel with a hole, but these were not experiments for the faint of heart. Virtually every experiment ended in an explosion of the steel. Look at this cylinder. It has a crack here where this steel exploded. So Hannay kept making thicker and thicker cylinders, which exploded at higher and higher temperature with more and more force. And one of these pressure devices like this, when it explodes open, makes a huge noise. And for this reason, the kind of pressure device is commonly called a pressure bomb. Hannay wrote about these experiments in wonderful prose. I want to read you one of his quotes. He said, "The continued strain on the nerves, watching the temperature of the furnace, and in a state of tension in case of an explosion, induces a nervous state which is extremely weakening. And when the explosion occurs, it sometimes shakes one so severely that sickness supervenes." Ultimately, after about 100 runs, Hannay found a few small diamonds inside the steel cylinder, and he promptly declared success and discontinued the dangerous work. I want to show you actual drawings of the Hannay diamonds. These are preserved today in the British Museum. They're real diamonds, but they're unequivocally natural, not synthetic stones. Historians now suspect that Hannay's workmen, perhaps they feared for the safety of the old man or maybe for themselves, but they planted diamonds to put an end to the project. And then there was Balthasar von Platen, who was perhaps the most colorful of all the would-be diamond makers. He was the kind of half-crazy inventor made popular in movies like Back to the Future. Well, late in the 1940s, von Platen came up with a scheme to synthesize diamonds, and he proposed to make giant 100-carat gems. He talked the Swedish General Electric company into supporting the effort. This was a logical move, since diamond dyes are the best way to pull thin tungsten filaments for light bulbs. Well, von Platen's idea was just wild. To make diamonds, you really need high temperatures and high pressures, so he designed what's called a split sphere device to focus a large force on a tiny area. That's high pressure. Let me show you his complicated assembly. Look at this. He starts with a golf ball-sized sample of carbon-rich material, and that was surrounded by a tennis ball-sized mass of thermite explosive. And all that material was gingerly wrapped in this copper cube. Now, each of 6 anvils like this one focuses a large force on one of the cube faces. So the whole assembly involves taking 6 of these anvils, each pressing against one cube face. The 6 anvils make a sphere. So here's the half-ton assembly, all 6 anvils pressing on the cube, and that is jacketed with copper. This whole device typically took a couple of months to assemble completely. Okay, then they had to immerse everything into a giant water tank that was pressurized to 6,000 atmosphere, and after all that they had to send an electric impulse to trigger the thermite for a few seconds of really high temperature and pressure. Then it took a long and tedious effort to open everything up. Often the parts would be damaged or destroyed in the process, and once in a while the thermite would fail to ignite, so the unwrapping process was a dangerous and a tense affair. Now there's been a lot of controversy about whether or not the ASEA team actually made diamonds. Some say they did it in 1953, but didn't realize it until some years later. In any case, that Van Platen device was much too cumbersome and dangerous to be widely adopted. In fact, it wasn't until the next year, in 1954, that a team of scientists at General Electric in Schenectady, New York, succeeded in developing the first unambiguous, simple, and reproducible process to synthesize diamonds. GE began their project Superpressure in 1951. They adopted a team approach with chemists and physicists, engineers all working together to make diamonds. They began by buying this huge press that generated 2,000 tons of force. And a lot of effort went into designing a device that concentrated all that force onto a small sample of carbon. After quite a few trials and errors, they settled on a simple and elegant design. This is called the belt apparatus. Here's a schematic diagram of the belt. You see those 2 gracefully curved pistons? They push against the sample. The sample is also surrounded by a belt of steel. Temperature was applied by passing a strong electrical current through the anvils and into the sample. The real breakthrough came in December of 1954 when they used the belt apparatus to make a few tiny diamond crystals. One of the inventors, chemist Tracy Hall, he described the excitement of the moment of discovery. I want to read you what he said. He said, "I broke open the sample after removing it from the belt. Instantly, my hands began to tremble. My heart beat wildly. My knees weakened and no longer gave support. Indescribable emotion overcame me, and I had to find a place to sit down. My eyes had caught the flashing light from dozens of triangular faces, and I knew that diamond had finally been made by man." Well, the GE scientists quickly confirmed the identity of the synthetic diamonds with X-rays. They found them to be identical to natural diamonds. Here are the original X-ray photographs from General Electric. It didn't take long to streamline the process and build more presses. They eventually built a factory with more than 100 presses like this one. And soon, GE was producing buckets of diamonds for use in diamond cutting and grinding tools. Today, more than 100 tons of synthetic diamond grit is produced every year. That's more carats of diamonds that have been mined since biblical times. And you may have noticed some of the everyday benefits of this vast new supply of diamonds. You can now buy 1-hour eyeglasses almost anywhere. Now that's amazing. When I was young, it took weeks to get a pair of glasses made, and it was expensive too. And you've probably also seen the way that diamond saws can surgically remove pieces of highway pavement. It used to be that road crews used noisy jackhammers which damaged the road while it was being repaired. And then there are all the abundant new varieties of polished stone that are being used for the exteriors of buildings and interior decorating. You might even have granite or marble facing in your home. That wasn't possible just 20 years ago. And something you probably haven't noticed. With diamond tools, it's much faster and cheaper to manufacture cars and other big-ticket items. And diamond tools provide greater accuracy and precision in the manufacture of parts. Let's shift focus now from carbon to another important substance. That's water. Solid water is remarkable for its many phase transformations. As temperature and pressure are varied, H2O molecules change their crystalline arrangement again and again. At least 10 different crystal structures are known, and you can watch one change to another in a heated diamond anvil cell. Look at this. The phase diagram of water shows the many different pressure temperature regimes where these forms of water are made. Isn't this amazing? Each of these Roman numerals denotes a different kind of water ice with a completely different structural arrangement of H2O molecules. Of course, not all phase transformations result in such drastic changes of crystal structure. In fact, sometimes the changes are rather subtle. One of my very first research projects was using a diamond anvil cell to study the structure of a brilliant red mineral called gillespite. And here's that actual crystal I worked on some 25 years ago while I was still at graduate school. You know, here's the really amazing thing about gillespite. At high pressures of about 20,000 atmospheres, it suddenly transforms to a deep blue color. The shape is exactly the same. You can go back and forth from red to blue as often as you like. It turns out that the color is due to a quantum jump of an electron in iron that's surrounded by 4 oxygen atoms. Here's a figure from my paper, my scientific paper. I found out that a slight buckling of this group of 5 atoms changes the energy of the quantum jump. And that buckling causes the change in the mineral's color. And the key point here is that the properties of materials are dependent on the arrangement of atoms. Okay, now we shift to the second topic of this lecture, chemical reactions. A chemical reaction occurs when 2 or more chemical substances combine to form a different compound, or when one chemical breaks down to other substances. Given the relatively small number of common chemical elements, there are really no more than about 80 in common use. It might seem that chemistry was a rather limited field. Apart from the unusual variety of carbon compounds, how many different combinations of elements could there be? Well, first, think about the number of combinations of just 2 different elements in a 1-to-1 ratio. Each of the elements, the 80 elements, can combine with any of the remaining 79 to give 80 times 79 divided by 2. That equals 3,160. You have to divide by 2 because combining element 1 with 2 is the same as combining 2 with 1. Now we need to try each of those combinations of 2 elements at many different ratios, 2-to-1, 3-to-1, and so forth. And you have to process the chemicals at many different temperatures and pressures. Those variations mean that there are literally millions of combinations and conditions to test just with 2 elements in combination. And then we have to consider a mixture of 3 elements or 4 elements or even more. Get this, there are more than 1 billion different 5-element combinations in a strict 1-to-1 to 1-to-1 to 1 ratio. And then you have all the variations, different ratios of elements, different pressure and temperature, different procedures for synthesizing new materials. There are literally trillions of combinations to try. It's simply impossible to test all the chemical combinations of the 80 common elements. The art of chemistry is to predict which chemical combinations will produce something new and useful. This isn't a random process. Chemical research is guided by the theory of chemical bonding and by hard-won empirical knowledge. After all, life is short. You don't want to waste time making useless stuff, and you certainly don't want to make dangerous chemicals in your lab. All chemical reactions involve the rearrangement of electrons through the breaking and reforming of chemical bonds. In every chemical reaction, some electrons move and some bonds are broken. While there are countless specific chemical reactions, and these reactions may seem to be infinitely varied, most reactions fall under a few general types. One of these is oxidation-reduction reactions. They include many of the common reactions with oxygen. Oxygen is that highly reactive gas that forms about 20% of the atmosphere. Oxidation reactions occur when oxygen or any other element that's eager to accept electrons reacts with an electron donor, such as a metal. Look at the periodic table. All of these elements near the right-hand side of the table are just 1 or 2 electrons short of a filled outer shell. They want more electrons, so they're especially good oxidizers. The chemical reaction called rusting, for example, involves the oxidation of iron metal. Iron plus oxygen goes to iron oxide. Burning is a more rapid form of oxidation. Burning commonly involves hydrocarbons or wood or some other carbon-rich fuel. Now, the products of burning invariably include hydrogen plus oxygen, or water, and CO2, carbon oxide. Those are the oxides of hydrogen and carbon. These and other familiar oxidation reactions release heat. There are several other oxidizing elements besides oxygen. Do you remember stories of the dangers faced by chemists who first tried to isolate fluorine? That element killed or injured several chemists in the 19th century. Well, fluorine is the strongest known oxidizing agent. Each fluorine atom wants an electron, so fluorine will rapidly oxidize almost anything it touches, including human tissues. Now, think about the opposite reaction, which is called reduction. Reduction involves atoms that give up electrons. Reduction reactions don't normally occur spontaneously in an oxygen-rich atmosphere, but sometimes they can be initiated in a hot fire. A fire consumes all the oxygen, so you're left with a reducing atmosphere in the hottest part of the flame. So you take iron oxide ores, and they used to be smelted in a fire by mixing the ore with lime, that's calcium oxide, and a hot burning charcoal in a furnace. So a typical reaction is iron oxide plus carbon goes to iron metal plus CO2. And the lime, that calcium oxide, it serves as a flux which lowers the melting temperature of the ore and thus speeds the reaction. This process has been used for thousands of years to make iron. All the oxidation-reduction reactions involve the movement of electrons. When iron metal is oxidized during rusting, the iron atoms lose electrons. When iron ore is reduced during smelting, the iron atoms gain electrons. This leads to the mnemonic oil rig: oxidation is loss, reduction is gain. All batteries rely on this transfer of electron. Look at this. There's a negative and a positive terminal of a battery. Let me show you what happens. When the terminal is in contact with a chemical such as zinc metal, which readily gives up electrons and enters solution as zinc N2 ions. Zinc becomes oxidized as the battery works. The positive terminal of the battery is in contact with a solution containing copper ions. That's Cu2+, that readily accept electrons. Copper becomes reduced, and it's deposited as copper metal on the positive terminal. You see the symmetry? When a circuit with the battery is closed, electrons flow from the battery's negative terminal through the circuit to the positive terminal. And the battery goes dead when all the electron donors and electron acceptors have been used up. For example, when all zinc atoms have entered the solution as Zn2+ ions, or all the copper ions have been deposited from solution as copper metal. In a rechargeable battery, like your car's battery, the chemicals can be reset by reversing the flow of electricity in a recharger. When we start talking about the chemistry of life, we'll see that all living organisms obtain their energy from oxidation-reduction reactions. On the one hand, plants take in carbon dioxide and water and use the energy in sunlight to reduce those chemicals. Electrons are moved from oxygen to reduce carbon and hydrogen. Animals, on the other hand, gain energy by oxidizing sugars and other chemicals that are produced by plants. Electrons move from carbon and hydrogen to oxygen. There's a very important kind of symmetry here. Lots of other kinds of chemical reactions occur in everyday life. Water and many other liquids have the ability to cause solution and precipitation reaction. Salt dissolves in fresh water, for example, to form a saltwater solution. And the flip side is that a saturated saltwater solution may evaporate to precipitate salt crystals. I'm sure you've experienced salt coating your body after swimming in the ocean. These kinds of reactions were absolutely critical to the advancement of chemistry, especially the classic methods of wet chemical analysis for rocks and minerals that were developed in the 19th century. These analytical methods involve careful sequences of solution and precipitation reactions to see different chemical elements and compounds dissolve at different rates so they can be separated by taking advantage of these reactions. Of special importance are the acids and the bases. Those are chemicals that alter the properties of water-based solutions. An acid is any chemical that produces positively charged hydrogen ions when added to water. So hydrochloric acid, HCl, for example, dissolves in water. It yields H+ and Cl- ions. Now, fruit is often rich in mild acids, such as citric acid, while car batteries use strong sulfuric acid. Acids are useful in all kinds of cleaning applications because they dissolve unwanted deposits. And then there are the bases, which include chemicals that produce negatively charged OH- ions when put in water. So sodium hydroxide, for example, it dissolves in water to form OH- and Na+ ions, sodium ions. Drain cleaners are among the strongest bases encountered in households. Now, when you mix them together, acids and bases tend to neutralize each other by forming water molecules. Look at this chemical equation. Sodium hydroxide plus hydrochloric acid goes to water plus NaCl. That's just salt. So antacids, like milk of magnesia, now that's magnesium hydroxide, they work in this way. The OH- neutralizes the excess H+ in the stomach. The strength of an acid or a base can be measured by the pH scale. On this scale, neutral water with equal amounts of H+ and OH- has a pH of 7. All water, even pure neutral water, has a measurable concentration of these two ions. Now, smaller numbers indicate an acidic solution, while larger numbers indicate a basic solution. Stomach acid typically has a pH around 2, while household ammonia has a pH close to around 11. There's another extremely important kind of chemical reaction I want to show you. And I have to start a little experiment here. What I'm going to do is mix these two chemicals, two liquids, in this jar here. I have to get more or less equal amounts of both of them. Let's see, that should just about do it. And stir that up. These are polymerization reactions I want to tell you about. They play a vital role in modern life. Polymers are the long, chain-like molecules that form from smaller molecules called monomers. These reactions happen in two common ways. First, you have addition polymerization. That occurs when monomers just join together end to end. A common example is shown here. It's polyethylene, in which individual ethylene molecules form a long chain. And then there's condensation polymerization. This process releases a molecule such as water or CO2 for each of the new monomers that's added. Now, this process often occurs when monomers have an exposed hydrogen atom on one end and an exposed OH or hydroxyl group at the other end. Pairs of monomers react, producing a single water molecule for each new bond that forms. Well, take a look at the experiment in progress. Just look at this. This is condensation polymerization in action. Now, all I did was mix two liquids. Product A and product B, they're called. This is polyurethane foam. And as each new polymer bond is formed, it releases a molecule of carbon dioxide gas. That's what causes this incredible foaming. Look at that, it's just great. Just from two liquids, each of which has monomers, single molecules that combine in this reaction. Now, you can buy this kind of polyurethane foam at the hardware store as insulation. Here's a can of this premixed polyurethane. There it goes. Now, the trick is that this is under pressure. This can's under pressure, so the polymer can't form until the pressure is released. Push the nozzle and out comes the foam. Some polymerization reactions like this one, or superglue or paint hardening, occur spontaneously. In fact, in this case, the reaction releases a lot of heat. You can feel that heat coming off. But other polymerization reactions, like cooking an egg, require heat. So there's a big range of behavior. The opposite reaction also occurs. The breakdown of a polymer into small molecules is called depolymerization. Cooking, marinating, they're common methods of depolymerizing or tenderizing meat. And that's important because most meat has tough polymer fibers in its raw form. Cooking also depolymerizes the fibers that give many plant stems and leaves their rigidity. You know that the longer you cook vegetables, the softer they get. Depolymerization is often a big problem in museums and in rare book libraries. So many historical artifacts are made of polymers. Curators have to work hard to prevent the depolymerization of historic documents and cloth, leather, other polymer-based artifacts. Now, refrigeration in an inert nitrogen atmosphere can slow the process, but nothing can reverse this natural process of decay. Well, in this lecture, we've seen that atoms rearrange themselves in two common ways to form new materials with new properties. First, phase transformations, such as the transformation of graphite to diamond, involve the structural reorganization of atoms. And second, chemical reactions involving the combination of several chemical substances to form new substances, or the breakdown of one chemical into other substances. Now, we'll return to chemical reactions in a few lectures as we investigate the chemistry of life. But in the next lecture, we'll examine some of the astonishing variety of the properties of materials.